This video is a walkthrough of answering an exam question. The only way to learn how to answer questions is by actually answering questions. It doesn't work to just passively absorb the ideas, you have to do it yourself. So as I go through this question, I'm going to put in breaks where I say, now pause the video, and you should go and work out your own answer with pen and paper. Then you can resume and see how your answer compares to mine. You'll need the question in front of you. Click on the link underneath this video and it'll take you to the question PDF. So let's get started. Here's the question. The first thing to do when you see an exam question is skim read it and look for keywords and figure out which section of the notes you should be thinking of. Here, skim reading, these are the words that catch my eye: prior density, posterior distribution, weighted sample. It's talking about Bayesian calculations. It's probably referring to section 7.1, and 7.1 talked about two ways of doing Bayesian stuff: mathematically, taught in section 4.2, and computationally, taught in section 5.2. Some other keywords: 95% posterior confidence interval. That was introduced in section 7.2, Bayes readouts. Next, look for question words. What is this question asking you to do? Find a density, identify a posterior distribution, calculate a confidence interval, find a posterior density, compute a confidence interval, generate a weighted sample from a density. Those are all the things that we're going to have to do. Again, it falls fairly squarely under section 7.1, 7.2, except for maybe the first bit, find a density. That should put you in mind of section 1.5 of the notes, where that was about likelihood and about calculating densities of random variables. Okay, let's dive in. Part 1. What is the prior density of the random variable capital theta? What do we know? We're told the distribution of theta. We're told theta is a Pareto random variable with parameters b0 and alpha 0. And this is the prior distribution we're using for theta. Stop and think. Ask yourself, how would I go about finding the prior density? This is the basic route that we used in section 1.5 of notes. To find a density, we'd write down the cumulative distribution function, probability that big theta less than or equals some value little theta. We differentiate it with respect to theta. The PDF is derivative of the CDF. So we better know what the CDF is. Happily, the question tells us at the bottom. It tells us if x is a random variable which is Pareto distributed with parameters b and alpha, then its cumulative distribution function is given by this formula here. Okay, so we can just differentiate it. The CDF, as it's written, it's got this indicator function. The indicator function may look a bit scary, especially if you're trying to differentiate. So what I'd do there is I'd split the formula into two cases and differentiate them each separately. And this is the answer we get. The thing I want to stress here is what I've drawn on the right is generic textbook results. I've written out, for example, the cumulative distribution function for a Pareto random variable big X, whereas on the left we have a random variable big theta. So be careful when you translate the symbols. Instead of x, we're talking about big theta. Instead of little x, we're talking about little theta. Instead of b and alpha, we're talking about b0 and alpha 0. I don't want to see any x's on the left-hand side. I don't want to see any x's in your answer. That's a dead giveaway that the student has just blindly copied without digesting what the material means. Next part. Show that the posterior distribution of theta is Pareto and give its parameters. Okay, this is a question about finding Bayesian posteriors. This is what we had from notes. This is the general procedure for finding a Bayesian posterior. Or at least this is the mathematical version of it. Let's just follow through the steps. Start with a probabilistic model for the data. Need to read the question, remind ourselves what is the model that the question tells us about the data. It tells us x1 up to xn are sampled independently from a uniform distribution between mu minus theta and mu plus theta. Okay, how do we find the likelihood for the data? The usual way we do all of these problems, I'll start out by writing the likelihood for a single one of the observations. The likelihood of little x given a value of theta is 1 on 2 theta times this indicator. It's a uniform in the range mu minus theta to mu plus theta. The length of that range is 2 theta, so I need to have a 1 on 2 theta. And I'm going to carry the indicator function around here. What we saw right at the beginning of the course, whenever we're trying to estimate parameters involved in the boundaries of a uniform distribution, it's useful to keep track of the boundaries explicitly in our algebra using an indicator function. One other little comment here. I've written the likelihood of x given that big theta equals little theta. There are two parameters here, mu and theta, but the question for part A tells us mu is known, theta is a random variable. So it doesn't make sense to condition on a known quantity. That's why I haven't written out mu in this likelihood statement. Next, we need to find the likelihood for the entire data set. This is a time for you to stop and think and figure out if you can work it out yourself. In fact, if you can work out the rest of the problem yourself. The likelihood of a collection of data points is the product of their likelihoods if they're independent, and the question does tell us that we're treating the x1 up to xn as independent. So this is just the product of all of those indicator functions. I've written it out slightly differently in the next step to simplify this product. For I ask myself, under what circumstances is the product over all I of those indicators equal to 1? The only way it's equal to 1 is if all of the x's lie in the range mu minus theta to mu plus theta, or equivalently, if the min of the x's is larger than mu minus theta and the max of the x's is less than mu plus theta. I'm just going to rewrite it once more. When we write mathematical equations, typically we're interested in an unknown, and it's good practice to write our equations to emphasize the role of the unknown. So here I've just rearranged it to put theta on the left to remind myself that I'm interested in this as a function of theta. Okay, we've written out the probabilistic model for the data. Next step, write down the prior likelihood of the unknown parameter theta. This we worked out in part 1. I'm just copying the formula that we had before. Good, that was easy. Next step, use Bayes' rule. Write down the posterior likelihood using Bayes' rule with this parameter kappa, constant kappa, and solve for kappa. There's nothing to it. We just write down the posterior likelihood of theta given the data is kappa times the formula we have for prior likelihood times the formula we have for the likelihood of the data. And solve for kappa. Okay, this looks quite horrendous. Normally we'd say, I want to choose kappa so that when I integrate this function with respect to theta, I end up with the answer 1. But I do not want to integrate that thing. There's another trick for finding kappas, and this is the time for you to stop and think. In particular, stop and think and look at this likelihood function and ask yourself, have you seen it before? The answer is yes, you have seen it before on just the previous line. Let's rewrite the prior likelihood in a generic form and draw the analogy with the equation we've got here. If x is a Pareto random variable, then the likelihood for x at value little x is constant times 1 on x to the power of alpha plus 1 times the indicator that x larger than or equal to b. This is just the general nature of the Pareto density. It's what we've written on the left-hand side, but just in different notation. And if we look at the posterior likelihood that we've got here, we can spot all these terms. We've got a 1 on theta to the power of something, and we've got indicators that theta is above or equal to something or other. All we need to do is simplify the algebra to push it, to coerce it into the standard form. Here I've written it kappa prime times 1 on theta to the whatever times the indicator that theta above or equal to whatever. Now this is the nifty thing about indicator functions. So I've got indicator that theta above or equal to b, indicator that theta above or equal to mu minus the min of the x's, indicator that theta above or equal to the max of the x's minus mu. The only way that I can get 1 out of multiplying those three indicators together is if all of the conditions are true simultaneously. In other words, if theta is above or equal to the maximum of those three values. Okay, so I've managed to pattern match our posterior density to a standard textbook density, so we can just state our posterior distribution is a Pareto distribution with these appropriate parameters. So that's it. The question asked us, show that the posterior distribution of theta is Pareto and give its parameters. And that's what we've just done here. Next, part 3. Calculate a 95% posterior confidence interval for theta. You should remember the relevant section from lecture notes here. This is the lecture note snippet about posterior confidence intervals. A posterior confidence interval is an interval such that the probability that the random variable lies in it is 95%. What do we know? First of all, we know the posterior distribution of theta. We know that the posterior distribution for theta is a Pareto with certain parameters. I don't want to write out complicated expressions, so I'm just going to say the posterior distribution is Pareto with parameters alpha 1 and b1. So we know the likelihood function, the posterior likelihood function. We'll plot it like these little diagrams from the textbook suggest we should. And then what do we do next? What I'm going to do is I'm going to choose a one-sided confidence interval. Generally, there's a choice about which confidence interval you want to report. Looking at the shape of the likelihood function here, it seems to me intuitively obvious we should try and keep the points with highest likelihood. So I'm going to declare that I'm going to give a 95% confidence interval of the form b1 up to some value high, and I need to calculate this value high. And the way I'll calculate it is by ensuring that the probability that theta lies in the range b1 up to high, given the data, is 95%. Theta has to lie above or equal to b1, so I don't need to include that side of the boundary in my formula here. Okay, now it's plain sailing. The question tells us the cumulative distribution function for a Pareto. We know that theta, given the data, is a Pareto, so I just plug it into the cumulative distribution function given in the question and solve for this high value. And this is the answer that we come out with. Okay, on to the next part, part B, part 1. Suppose mu and theta are both unknown, using a normal as the prior for mu and a Pareto as the prior for theta. Find the joint posterior density of the two parameters. I'm just going to refresh our memory about the universal steps for every Bayesian question, or at least for every Bayesian maths question. Start with the probabilistic model, write down the prior likelihood, use Bayes' rule to write down the posterior likelihood, and then reason about the posterior. One slight thing to worry about, this generic formula from notes, theta there is a stand-in for all of the unknown parameters in the question. In this particular question, we've got two parameters, mu and theta. The uppercase version of mu looks like the English letter capital M, so that's why I've written m comma theta. It's really a capital mu comma capital theta. Slightly confusing that the textbook refers to theta to refer to all unknowns, whereas here theta is just one of the two unknowns. This is something you always have to watch out for. Make sure that you're translating the lecture note general results into the particular problem with care. We start with a probabilistic model for the data. This is exactly what we had last time. Write down the prior likelihood. Okay, now this is a time for you to stop and think. See if you can figure out what the prior likelihood is. The question just says use a normal as the prior for mu and a Pareto as the prior for theta. But we want the prior for the pair of random variables. That's what the general procedure is always says to do. The question doesn't tell us a prior for the pair mu comma theta. What we'll do is we'll assume that mu and theta are independent under the prior distribution. The question doesn't say that. General guideline is if a question doesn't tell you two random variables are not independent, it's safe to assume they are independent, and you should just write that down. So if they're independent, the joint likelihood is the product of the individual likelihoods, and we can just fill it in. Likelihood for a normal times likelihood for a Pareto. Next step, use Bayes' rule. Always the same. The posterior likelihood of the unknown parameters mu and theta is kappa times the prior likelihood times the data likelihood. We don't have to simplify. I've done a tiny little bit of simplification here. The question tells us leave your answer as an unnormalized density function, so we can just copy it out and leave the kappa in there. If I thought I was going to need this answer later on, then I would have simplified it further to make life easier for myself. Okay, next part, part 2. Give pseudocode to generate a weighted sample from this density. Your code should produce a list of m sampled pairs, mu1, theta1, dot, 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 mu m, theta m, together with weights w1 up to wm. What's it talking about when it says generate a weighted sample? Well, this is just a reference to the computational Bayesian procedure. We start with a probabilistic model. We take a prior sample theta1 up to theta n from the prior distribution. We compute weights. We compute a different weight for each one of the sample points and rescale the weights so they're summed to 1. Again, this is slightly confusing. The general recipe in the notes refers to theta, and by theta it means all of the unknowns in the question, whereas this specific question has two unknowns, mu and theta, so it's confusing that there is this notation mismatch. That's probably part of what the question's asking. See if you can deal with notation mismatch. So what do we do? Start with the probabilistic model. That's what the first step of the recipe is. We've done this already. This is from our previous answer. Next, take a sample from the prior. We're told what the prior is. The prior is mu is normally distributed with mean C0, variance sigma naught squared. Theta is Pareto with parameters B0 and alpha naught. As we did in the previous part, we shall assume that they're independent because we're not told otherwise. Next step, how do we take a sample from this prior distribution? In particular, how do we get a list of sampled pairs? I'm simply going to get a list of mu samples and a list of theta samples, and then I'll zip the two together. We're assuming that mu and theta are independent, so we'll generate them independently, but the question asks us to produce a list of sample pairs, so there's just one way to achieve that. Next, we've got to compute weights from the data likelihood. There's another point to stop and think. What code would you write to compute the weights? Here's some code. All we need to do is we need to implement that likelihood function in code, and more concretely, we need to evaluate the likelihood function, likelihood of x1 up to xn given mu and theta. We need to evaluate it at every single one of our sampled points, mu, theta. The way I've written it here, it's NumPy vectorized code. It's quite terse, quite dense. This is a vectorized operation. What this code does is that for every mu, theta pair in the list of samples, it's going to work out the data likelihood. So I end up with a vector w the same length as the list of theta samples. In an exam, if you're not used to NumPy vectorized code, I suggest you write it out as a for loop or as a list comprehension statement, whatever you're most comfortable with. Okay, so that's this part of the question. It told us produce a list of m sampled pairs together with weights, and that's what we've just done. On to part 3. Give pseudocode to find a 95% posterior confidence interval for theta. We looked at this before. We reminded ourselves of what lecture notes had to say about posterior confidence intervals. The difference here is that it's asking for pseudocode. So in other words, it's asking for the computational strategy for finding a posterior confidence interval. This is what we're trying to do. We're trying to find an interval, let's call it low, high, such that the probability that our random variable lies in that interval, the conditional probability given the data, is 95%. That's what we mean by a posterior confidence interval. So, stop and think. How would you go about doing this? Bearing in mind what we've already got. We've got a list of theta samples and we've got their weights. This is a bit more detail about what we might like to do. We're going to, for example, take the standard symmetrical confidence interval. I want to pick a value low such that the probability that theta less than low is 2.5%, probability that theta less than high is 97.5%. There's a sketch of the posterior likelihood for theta. You may be wondering why I'm looking at a two-sided confidence interval here, whereas back in part A we chose a one-sided confidence interval. It's simply, I have no idea what the likelihood function looks like, so I'm choosing two-sided as a simple default action. In part A, we had a formula for the likelihood, and it was very easy to see that it should be one-sided. In this case, I don't know what it is. If I had a computer, I'd plot the likelihood and I'd possibly change my decision based on that. Okay, that's more detail about what we want. How could we achieve this in code? Basically, we want to find low such that 2.5% of the mass is associated with values less than low. Simple way to do that, take our theta sampled values, a list of theta 1 up to theta m, sort them in order of increasing theta, and find the first point at which the cumulative sum of the weights just touches 2.5%. Similarly for high. There's just one little subtlety worth drawing out here. We found a sample with posterior weights of the pair mu comma theta, whereas what we're trying to find out here is a confidence interval just for theta. There's this slight subtlety about how do we go from finding a posterior for a pair of random variables to reporting on just one of them. In this computational answer, that basically just comes for free. We don't need to even think about how we're ignoring mu, we're just ignoring it. Have a look at the video for section 7.1 to see a bit more discussion on this point. Two other notes about exam strategy. This question asks for a confidence interval. Don't bother about rounding. Don't bother about these, do I mean theta less than or equal to low, or do I mean theta less than low? We didn't bother about that in lecture notes. There are ways to be meticulous about it, but if you have a decent sized set of samples, it's not going to be an issue, unless you're working with discrete random variables, in which case this confidence interval strategy is not quite the right thing anyway. The other thing, I gave my answer in pseudocode. I had lots of English in there, it's not really NumPy. Don't bother about getting NumPy syntax exactly right. This is an exam, it's not a coding test. Okay, so finish the question. Before we go, one thing you should do after finishing a question, reread the whole question and ask yourself, what's the theme? What are the examiners getting at by setting this? Several things that we might pull out here. First of all, what's the whole point of the question? We've been answering it very much by the book as a collection of formulae and procedures, but let's think about what this question's here for. This is the sort of picture that we have in mind, where we've got a sequence of readings, x1 up to xn, and we're trying to fit the theta, the size of the interval that we think they all come from. You could imagine all sorts of applications for this, wanting to estimate tolerances, deviations, and so on. So that's why the question is here in the first place. What are the things that the examiners might be looking for in our answers? Here's another theme that we might pull out. Look at part B, parts 1 and 2. We found a joint posterior density, mathematically, and then we found a joint posterior density computationally. So one of the themes here is the maths versus the computational approach to Bayes' theorem. And there's a subtext here. In B part 1, we couldn't do anything. It just said leave your answer as an unnormalized density. In B part 2, we could actually get a useful thing, which we could then go on and use to find a confidence interval. So that could be another theme, that, hey, the maths is often, doesn't get us as far as we want to go to, we've got computers instead. Just stick in a remark along those lines in your answer and the examiner will be delighted to see you've thought about it. Another point, I'll call it accurate translation or serenity. There's actually been very little creative thought needed in this question about novel ways to solve things. The bulk of this question has just been, here's a procedure from notes, here's the specific question we're tackling. They use different notation, sometimes confusingly they use the same symbol, but they're talking about different things. Can you translate accurately? If the examiner thinks that you've just been copying formulae without thinking about them, they'll be very unhappy. Finally, double check you've answered all the parts. I always say this, there are always some students who just forget to answer one of the pieces.